graph it. So if you graph this thing, you could graph polar by hand.
Yes.
You need a lot of points. Because if you don't use a lot of points, what happens? You don't know what the arc looks like. Like, it'll jump around, and you're like, I don't know if it's a pedal or did it invert. You know, it's hard. It's not easy. Also, if you're doing a lot of trig calculations, it's tedious. So there's one, and then there's the... Oh, they're right there. So let's get this into our notes. But then it says find the area outside r equals 2 cosine theta and inside r equals 1 plus. What is this right here? Anybody know what that is?
Circle.
Yeah, what is that? That if you square it, what do you end up with? R squared is 4 cosine squared theta, right? Is that correct? You know in polar land that x squared plus y squared is equal to what?
What?
R squared. R squared. So in this case, x squared plus y squared is equal to what? 4 cosine theta. So you can go and translate this into, try to translate this into something else. It is possible. Cosine squared, yes, cosine squared. And then there is some more work you can do to get an idea of what the Cartesian looks like. You can flounder around, but you don't really need to do that because do you have to go to Cartesian in order to compute this area?
No.
Is it possible to do that? Could you go to Cartesian, compute the area that way? Yeah, but what's the point of having another way to write functions like this?
Easier.
To make it easier for yourself. In Algebra 2, for example, when we start dealing with different ways to write lines, I tend to see kids go back to slope-intercept all the time. Do you need to go to slope-intercept all the time? No. Do you need to go to Cartesian all the time? No. Absolutely not. It feels nice because you're like, oh, x squared plus y squared is equal to 4 cosine squared theta, but then you're like, theta, x, and y, and then I have to remember a formula that maybe I don't remember, and then it gets worse. Don't make it worse for yourself. So first of all, which one of these is 2 cosine theta?
The one on the inside.
The one on the inside. Exactly. So that's this one, and I'll do a nice shading here. This right here is this one right here. And inside 1 plus cosine theta. So that's going to be the other one. 1 plus cosine theta. So it's this one right here. What's the first thing you notice about the shape of this thing? What do you notice? It's like it's cardioid, yeah. Which from cardiac, yeah. It is like a heart, it's named as such. But what else do you know about the structure of the shape?
It's symmetric.
It's symmetric. That's really key because it makes your integrations a little bit easier. So instead of going all the way around, we only need to do it half of it and then multiply it by 2. The key thing to realize here, and I'll zoom in real far here, if you were going to draw the shapes here, it looks a little strange because instead of rectangles, what are we dealing with? Sectors, right? So for example, let's say that purple one wasn't there and we just wanted the area inside the cardioid, the green. Each of the slices would look like, let's say, here's one of the sectors, right, that you're sweeping out. But we're not going to keep all of that because we're cutting out the purple area in the middle. So instead, we're cutting it off right there, and we're just looking at that. Area between two curves, when we had rectangles, it was just the larger one minus the smaller one. So what are we doing here? Larger one minus the smaller one. The perspective change you have to have is your base is always at the origin. It's not over here. It's not up and down vertically. Vertically, in this sense, is any line that goes through the origin is on that path. So how are we going to set this up? It's going to be, so what was that general formula? 1/2 alpha to beta of what?
Alpha theta squared.
R squared d theta, right? In this case, because there are two functions, it's going to be 1/2 alpha to beta of R1 theta minus R2 of theta, quantity what? Do you square it here or do you square each of them individually? Individually. You made that, that's a potential mistake you can make just with rectangles, right? You don't square the sum, you square them individually, not together. Correct. It's two integrals that you're gluing together. So I don't want to put parentheses around the whole thing, so it's going to be each of these squared. Then what?
D theta.
d theta. This is just two integrals glued together. You're cutting out the middle circle-ish thing from the cardioid. So do we have, what does R1 represent? The outer one, and this is the inner one. As a side note, what was one thing you always had to be careful of when you were determining which curve was below and which curve was above? There was something that came up sometimes that you had to be careful of. They could cross, right? They could switch. Does it ever switch here?
No.
Because of that, do we ever have to find any intersection points? No, we don't. That's kind of nice. Is it possible for these things to weave in and out of each other?
Absolutely.
Totally. And what happens if you integrate across without breaking it apart into separate?
Because it's negative.
It starts canceling, right? So you end up with an answer that the algebra is correct, but the setup is not correct. So in this case, which one is R1 going to be? What is the green one?
1 minus cosine.
I think it's 1 plus cosine theta. And what is R2 going to be? That's R2 of theta and of theta. What is it?
2 cosine.
2 cosine theta. So you take both of these, plug it in, and what's the last thing we need to determine that we haven't yet?
Alpha, beta.
In this case, what's alpha going to be? Where's it going to start? 0. And what's beta going to be?
2 pi.
Is it 2 pi or pi? It's pi. You can think about it when you look at the shape. You're starting at the x-axis, which is theta equals 0. But then where do you need to get to? You need to get back all the way to the origin. So where, look, you have these points, that point, that point, that point. If you stopped at pi over 2, would you have done all of it? If you stop at pi over 2, how much are you going to have? You're just going to have this part of the region. But you need to have a little bit more, right? You need to have a little bit more. So what do we think this integral should be?
Actually, I thought you were asking the whole thing.
It is. We're gonna double it in a second. Yeah. So yeah, I'm just saying. Excuse me. Matt asked a really good question. The way we're attacking this is we're just gonna do the upper half, and then what? Do what?
Multiply by 2.
Multiplied by 2. That's why I'm stopping at pi.
Yeah.
Sorry. No. I was not clear with my question. You're absolutely right.
We're doing the whole thing. Do we stop at 2 pi?
We are doing the whole thing because what we're gonna do is we're gonna double just the upper half.
What if you just start the whole thing directly?
Oh yeah. If you want, functionally it doesn't really change much here because the math is going to be very similar. So in this case, yes, you could go, if you're going to go all the way around, go to what? 2 pi. That's fine. So if we were going to set this up, it's going to be 1/2 0 to 2 pi of what is it? 1 plus cosine theta squared plus 2 cosine theta squared d theta. Oh, is it minus? Yeah, it is minus.
Wait, why is that?
Because they want, you can either go from 0 to pi and double it, or just go all the way around. In this case, it doesn't change much, difficulty-wise. Because, is that an integral you're going to do by hand?
No.
No. It really doesn't change much because you are going to plug that into your calculator and go, help me please. Cosine squared, another cosine squared, blah, it's parts. Busy work. What is it, 1/8? Is that what it said? 1/8 of a circle? So we have this. That would be pi over 4, but that's not what we want. We want pi over what? 8, because it's in...
No.
Oh, no, it's 1/8 of a circle.
Yeah.
Sorry, excuse me. That is what you want. And then you have this. What's the radius? 1, right. So they want you to describe this region with inequalities, right? So R. What's the lowest value R can be, and what's the biggest value R can be?
0 to 1.
0 to 1. Because if you're looking at the set of all of these points right here, if you were going to put them all in a set, what's the lowest R value? 0. What's the furthest you can get from the origin? 1. Now, the theta value is also pretty straightforward. What's the smallest theta value?
0.
And it goes all the way up to? So, describing a pizza wedge with polar coordinates, nice. Nice. Ah, where does it get more fun? Rectangular coordinates, right? So you want to describe these in rectangular coordinates. How are you going to do that? Jesse, and then Brendan. Yeah, what'd you do?
I used, should I just say what?
Yeah, tell you what'd you do?
I just used the pi over 4 line. I used the square root of x squared plus y squared.
So
I just kind of thought through it.
Okay, well hold on a sec. You know that what does R equal? The square root of what? X squared plus
y squared.
Y squared. So what do you now know? You know that 0. So you know that that has to be between You know that has to be true, right?
Yeah.
Now, is that enough, is the question. Is that enough? If you graph this inequality without anything else, if you graph that inequality without anything else, what do you get? Can anybody tell me what you get?
Something like this.
You get the whole circle, because this right here is a circle of radius 1. So that represents all of the points inside and including the edge of a circle of radius 1. So this right here is too much, right? It's getting us in the right direction, though. What else would we need to limit? So you know that y has to be less than or equal to x, right? Because what line is that? That's this line right... This line right here is what?
Because the correlation point
Y
is
equals
that-
X.
Y equals x, right. So now what do we have? We have the circle down less than this, right? But what else do we need now? There's one more that we need. And y has to be greater than what? There it is. There's your pizza slice. Not so trivial. It's a lot easier to write it in polar form.
So that's complete.
Yep. Here we go. For the curve r equals f theta from... Oh, nice. Show that that's the arc length. Awesome. Okay, so what you need when you're doing the arc length of a polar is you need dx, d theta, and you need what else?
dy dθ.
dy d theta. So they tell you that r is equal to f theta, correct?
Yeah.
But you know that x is equal to r cosine theta and y is equal to r sine theta. So what does that mean? It means that x is equal to f theta cosine theta and y is equal to f theta sine theta. So now that you have x in terms of theta and y in terms of theta, what can you find?
Derivative.
Derivative, yeah. So what is dx d theta going to be? And what do you have to use?
Product.
Product rule. The derivative of the first times the second plus the first times the derivative of the second. Is it really easy to mess up the signs? Be careful, because if you don't, the identities won't apply and this thing won't simplify. What is dy d theta going to be? F prime theta sine theta plus f theta cosine theta. Exactly. So now, what do you have to do to those things?
Square them.
Square them, add them together, and take the square root. If you do this properly, it works. I'm not doing it now. What identity are you going to apply over and over again?
Sine squared plus cosine.
Yeah, you're going to apply sine squared plus cosine squared is equal to 1. I'm not going to do that out right now. I'm not going to do out the algebra. If you want to work through the algebra, you can, or I can check your algebra later. But it's just algebra at this point. You just have to be careful about the squaring. That's it. A lot of sine cosines are good. When you see sine times cosine and you have to integrate, you hope that they cancel out. And they do. A lot of them do. Just be careful. Okay, put everything in it. So in this case, do you remember how we stated this? You can't just plug in infinity, right? What do you have to introduce to the integral structure? A limit. You're going to rewrite this as the limit as b approaches infinity of what? From 1 to of 1 over x squared dx. So you run this, you write the integral, and then you run it as a limit. You run it as a limit. That's the only thing that changes. So that's the first type of improper integral. Let's do this one. Actually, you know what? You practice it. Do that one out right there. Do that one out. Oh, okay. So this is going to be the limit as b goes to infinity of what? Negative x to the, from what to what? 1 to b. So you just have to be careful of all the negative signs. Yeah, I know. You could do this, and then you could say it's, negative 1 over x from 1 to b. That's fine. So what's that going to be? The limit as b goes to infinity of what? Negative 1 over b minus
Plus x.
minus negative what? 1. Yeah, so it's going to be plus 1, right? So as this goes to infinity, it's going to go to what? 1. Nice. That's kind of cool. Just be careful. B goes to what? 2 from the what? The left, right? So what do we end up with? We end up with the limit as b goes to 2 from the left of negative 1 over b minus 2 plus, or sorry, minus a what? Minus a half. So we're really now just concerned with this right here. We've broken this down to investigating what happens there. What happens as b goes to 2 from the left? What does this go to?
Infinity.
Does it go to infinity or negative infinity? Yeah, because the top is negative. If you're left of 2 and you subtract 2, it's always going to be negative. This right here goes to 0 from the left.
You have negative 1.
Exactly, so negative over negative is going to be a. So this comes down to, oh, minus a half. Okay, so what do we know now? What do we now have proved? What have we proven?
This is no bound.
There's no bound. There's no bound to this. So just because something, volcanoes, like you have to be very careful about these, but you can prove these with limits. You can prove them with limits. You know that if you have the integral from a to b of f of x dx, that's equal to the integral from a to c of f of x dx plus what? The integral from c to b of f of x dx. Does it matter if c is between a and b? It actually doesn't. C does not have to be between a and b for this to be the case. It does not. I can draw you the picture, but if you go farther, it means you have to double back. And if you double back on an integral, it cancels itself out. So here's the thing. You can split this apart. Where do you want to split it on this one?
0.
Yeah, you know that this, you want to split it into negative 1 to 0 of 1 over x to the 4th dx, and then add what to it? 0 to 2 of 1 over x to the 4th dx. How many improper integrals do we now have?
2.
We have 2 improper integrals. We can compute both. If one of them diverges and the other one doesn't, the whole thing diverges. But if both of them do converge, you can add them together and you have an answer. So keep in mind you can split these apart. Okay, your homework tonight is working with improper integrals. It should be a refresher, generally speaking.